In this video, we're going to go over section 6.1 from our textbook, which is on one-to-one functions and inverse functions. So a function f is said to be a one-to-one function if, for elements a and b from our domain of f, if a does not equal to b, then this implies f of a is not equal to f of b. Okay? So we'll look at two examples here. We have y is equal to 6x minus 2, and we want to figure out if this function is one-to-one. Now notice, this here means that if f of a is then equal to f of b, then this implies that a is equal to b. So in this example here, if f of a is equal to f of b, plugging a into our function here, we'll have 6a minus 2, and then plugging b into our function, we'll have 6b minus 2 here. Notice that these 2's cancel. If we add 2 on both sides, these guys cancel, and so we'll get 6a is equal to 6b, and then the 6's cancel, and we therefore get that a is equal to b. So this tells us that this function here is one-to-one, okay? Just using this fact here. Now on the other hand, looking at this example here, what we'll do in this case is pick values for a and b. So we'll let a be equal to 2 in this case, and b be equal to negative 2 here. Now we can clearly see that a is not equal to b, since 2 is not equal to negative 2 here. So we'll plug in 2 into our function. This will give us 2 squared minus 4. This is 4 minus 4, which is equal to 0. Doing the same thing, plugging in negative 2 into our function, we'll get negative 2 squared minus 4, which is 4 minus 4, which is equal to 0. So here we have a is not equal to b, but we just showed that f of a is equal to f of b. We got 0 for both of these guys. So this tells us this function is not one-to-one. So another way to think about this, a function is called one-to-one if each output has only one input. So that would be a one-to-one function. And so we'll look at these examples right here. We have this guy, f of x is equal to 3x, and as we can see here, every output here only has exactly one input. So the only value that'll give us negative 6, for example, is negative 2. The only value that'll give us negative 3 is going to be negative 1, and so on and so forth. So that means this guy is one-to-one. Moving on to this here, x squared, notice that negative 2 gives us 4, but positive 2 also gives us 4. So in this case, we have one output, which is 4, but this output 4 is produced by 2 separate inputs. Right? So this tells us this function is not one-to-one. We said each output has to have only one input. Similarly, the output 1 here also has 2 inputs, negative 1 and 1. So this function is not one-to-one. And lastly, x cubed here, we can see that all of these outputs have only one input. So negative 8 can only be produced from negative 2, negative 1 can only be produced from negative 1, and so on. So this guy is one-to-one. Now one way to figure out if a function is one-to-one is by a horizontal line test. So a function is going to be one-to-one if every horizontal line will intersect the graph of the function at most one point. So similar to the vertical line test, but now we're doing a horizontal one. So these are the graphs of the functions up here. Now if we were to do the horizontal line test, so we're just going to draw a bunch of horizontal lines like this on our graph. And as we can see, every single one of these lines only intersects our graph at one point here. We already know that this function is one-to-one, but the horizontal line test confirms it as well. Similarly, for x squared here, we draw a bunch of horizontal lines on the graph here. We see that these horizontal lines are intersecting our graph at 2 points, here and here, here and here, for each of these horizontal lines that we draw. So this guy is not one-to-one by our horizontal line test, and we also confirm that by looking at these output values here. And lastly, looking at the graph for x cubed, we draw a bunch of horizontal lines here. We see that they're only intersecting our graph at 1 point for every horizontal line drawn. So this guy is one-to-one, and we also saw that by looking at the table here. So this brings us to inverse functions. So addition and subtraction are inverse operations, as are multiplication and division. For example, if we start with a number x, then multiply it by 8, and then dividing it by 8, this will give us x back as the result. So this tells us these two functions, 8x and x over 8, are inverses of each other with respect to function composition. So essentially, inverses undo each other. Inverse functions undo these operations. And if f is going to be a one-to-one function, then g is going to be the inverse function of f, and f is going to be the inverse function of g. If we plug g of x into our function f of x, we will get x back. And similarly, if we plug our function f of x into g of x, this gives us x back. So this is what we mean by these functions being inverses of each other with respect to function composition. Now, something to note here is that a function must be one-to-one in order to find its inverse. Okay? So let's look at this example here. We want to determine if these functions f and g are inverses of each other. So we can do so by just making sure that this is true, that both of these are true. We need this to be true and this to be true. So first we'll look at the composition of functions of f of g of x. So this just means we need to plug g of x into our function f of x. So we're going to plug in our entire g of x into f of x wherever we see an x here. So we get 4 times x over 4 plus 3 minus 12. Okay. So this 4 will multiply both terms in our parentheses here. So these guys will cancel. So we'll get x plus 4 times 3, which is 12, minus 12. So we get x here. So this first one is satisfied. Now we gotta look at the next one here. We're gonna look at g of f of x. So we're gonna plug our function f of x into g of x wherever we see an x value. So we'll plug this whole thing into this x here. So we'll get 4x minus 12 divided by 4 plus 3. This is equal to 4x over 4 minus 12 over 4 plus 3. So here we get x minus 3 plus 3, and we get x back. So this tells us that yes, f and g are inverses. Alright, so now we want to find some inverse functions. So we're going to introduce some notation here. The notation for the inverse function here is read as f inverse. So it's not f to the negative 1 power, it's the inverse of f, or f inverse. Now by the domain of inverse functions, by the definition of inverse function, the domain of f is going to be equal to the range of f inverse, and the range of f is equal to the domain of f inverse. So this diagram here, we have the domain of f here is equal to the range of our inverse, and the range of our function is equal to the domain of the inverse. Right? This is because our inverse is undoing our function. Okay? So let's look at this example here. We want to find the inverse of this guy here. So recall we said that a function must be one-to-one in order to find its inverse. So the first thing we want to do is make sure that the function is in fact one-to-one. And in the interest of time, I've put this table and this graph here. So we can easily check that this function is one-to-one. This is the graph of our function. We can check this by looking at our table here and making sure that each output has exactly one input. And it looks like that is the case here. We can also use our graph and do the horizontal line test. So we draw a bunch of horizontal lines on this graph here and make sure that these lines only intersect our graph at exactly one point here. So we see that the horizontal line test and looking at the input and outputs in this table here tell us that this function is one-to-one. So this tells us that our function will have an inverse. So the next thing we want to do, the next step to find this inverse, is we're going to rewrite our f of x as y and then solve for x. So we'll rewrite this guy as y, so we'll get y is equal to 5x plus 2. And then we want to solve for x. So we'll take away 2 on both sides. So we'll get y minus 2 is equal to 5x here. And then we'll divide by 5 on both sides. So this tells us that x is equal to y minus 2 over 5. Now the next thing that we want to do is we're going to switch our x and y values. And this makes sense because, again, our inverse functions undo each other. So we need to switch our variables here. We're going to switch our inputs and our output values because, like we said here, the domain of f is equal to the range of our inverse, and the range of f is equal to the domain of our inverse. So we're going to switch our input and output values. So we get y is equal to x minus 2 over 5. So this tells us, writing it with our new notation, the inverse of f is equal to x minus 2 over 5. All right, so let's look at just one more example here. We have this function here, x squared plus 1 over 2, and we want to find the inverse of this guy. And I'll tell you that this one is one-to-one, so we can skip that step here and proceed with our second step. So we're going to rewrite f of x as y, and then we want to solve for x. So we'll multiply by 2 on both sides, so that guy cancels. So we get 2y is equal to x squared plus 1. And then we'll take away 1 on both sides. 2y minus 1 is equal to x squared. And lastly, we need to get x completely alone. So to get rid of the square here, we'll square root both sides. So we get the square root of 2y minus 1 is equal to x. And then remember, we need to switch our x and y's. So this tells us that y is equal to the square root of 2x minus 1. And we can conclude that the inverse function of the inverse of f is given by the square root of 2x minus 1. All right, so that's it for this video.